piece of iron and make it into that. And we're going to drop it into a solution of silver nitrate. And what we're going to start to see is we're going to start to see crystal growth along the surface of this. You can see it with your eyes. You got a dirty piece of iron, and all of a sudden you're going to start to see crystal growing on it. What is that crystal? Silver. So you are silver plating this iron. Okay? So this is a way to silver plate. She takes some silly jewelry, makes it cheap, and then just puts a light layer of silver around it, right? A lot of the women's costume jewelry is like this. I mean, probably not your wedding ring, right? Because you're washing dishes with your wedding ring, going swimming with it, playing kids with it, and whatever. But something that you might only wear an hour or two at a time, gold-plated, silver-plated is the way to go. What about this? Now, what if, even though this would be silly, if she had a silver ring and wanted to iron plate it? Could she? Why not? Brittany's saying no. Well, first, which one has to be on the top? The thing by itself or iron? Thing by itself. So is silver on top of iron? So is this reaction going to run? No, there ain't no way. All right. So she could take her sterling silver earrings and put it in iron nitrate and let it set for 4 days. Nothing's going to happen. Nothing. Just going to sit there. So now when people start asking you these questions, well, is this or this going to react? Well, now you have two reaction classes. And by the time you finish organic, of course, you're going to have hundreds of them. But right now, I mean, we've got to start somewhere. Now you may say, well, how can you gold plate? Look at this here. How can you gold plate? Can you gold plate? Tell me something that you can gold plate. Well, you can't. But when you get into, not this next chemistry, but the next one in January, you guys will be up for it if you take me. You know how you can change these reaction arrows sometimes? By running electricity through them. That's why they call it electroplating. All right? So there are ways to change reactions that don't happen spontaneously by putting energy into them. All right? So we can, have you ever heard of electroplating? I mean, you can electroplate it out. Okay? Not peaceful and naturally. You got to have high voltage and all this, but it can be done. Look here. What about lead and magnesium chloride? What's going to happen? Nothing. She says it won't work. Why? Because lead has to be on top of the magnesium. Well, here's lead. Here's the magnesium. Is lead on the top? There ain't no way. That ain't going to work. No reaction. How about the other way around? What's this going to give you? She's going to give me a magnesium what? Chloride and lead. So what Sandy did here? What's she growing? What's going to be the crystals? The lead. So if you had a reason, right? I mean, which scientists, engineers, chemists think sometimes they got reasons to do things. All right. I don't know what that would be. But if you wanted to put all that lead on top of magnesium, that'd be a wonderful way to do it, right? I don't know why you would do that. Maybe you wanted to get rid of the lead, right? Because now your lead's in a solid form. So at least you can see it and dispose of it. And then what can you do with the liquid? Just dump it down the drain, maybe. I don't know, right? So that way you don't have a whole volume of liquid to send off to the hazardous waste people. You just have the little piece of lead metal to send off to the hazardous waste people, right? Okay. Who's happy? Who's not happy with this? Single replacement reactions. These are all single replacements. A telltale sign is you will always have a bare metal. That means something that does not have a ligand on it, something that does not have a nitrate, a sulfate, a borate, some polyatomic on it. Now people, let me ask you, silver nitrate plus iron, is this a single replacement reaction? Yeah. When we look at reactions, we look at left-hand sides and we look at right-hand side. It does not matter that these two things are switched. All right. I just kind of did that for you as we're getting started here. You can switch them apart. Well, what about if you've got something producing CO2 and water? Could it also produce H2O and C2O? I mean H2O and CO2? Sure it could. When you look at chemical reactions, what's important is that if it's a reactant, it's got to be on which side? The left side. The left side, right? And if it's a product, it's got to be on the right side. The order does not matter. All right? The order does not matter. Just you have to pay attention to your sides. All right, we ready to do one more class and call it a quits? One more reaction. Well, if these are single replacements, what do you think the other one's going to be called? Double replacements. Wonderful. So these are called double replacement reactions, and some books call these, I think in the book you'll be using next time, they call it a metathesis reaction, but they are the same thing. Okay. Now, here's an example. Sodium chloride plus silver nitrate gives me something another. Okay. Here's one. Lead nitrate, lead 2 nitrate, plus potassium iodide gives me something another. All right. And let's do one more. Let's do potassium chloride plus sodium iodide gives me something another. Now, before we start talking about these, we have to talk about solubility, because these things all depend on how soluble something is in water. Now, what would happen if you take sodium chloride and put that in water? You take table salt, put it in water, stir it up, what's going to happen? It's going to dissolve. Okay? And we consider that a 100% ionization. In other words, it dissolves 100%. So in this classroom here, you have two options. It will dissolve or it won't. It is a very black and white scenario. Okay? Now, in real life, it's not black and white scenario. Here's an example. Let's take gasoline and water. If we mix that and we let it sit, will the gasoline and water separate? Yeah, into two separate layers, right? Which layer will be on the top? Does anybody know? The gasoline layer will be on the top, water layer will be on the bottom. Now, if I take a straw and stick down in that water layer, and I tell John to suck on that straw, is he going to have gasoline taste in his mouth? Yes. Because gasoline, even though it is separated, has a partial solubility. I mean, you will find it in there, okay? Not a magnitude, not a whole gob, but it will be there, okay? But we're not going to answer those type questions. That's far too much math for right now. We're going to answer whether the thing dissolve, yes, no. Are you with me? Okay. Now, what's going to happen here? Double replacement. You've got a positive end of this compound and a minus end, a positive end and a minus end. Now, what if they switch partners? Okay? So we got a boyfriend and girlfriend, we got a boyfriend and girlfriend, they're going to switch partners. What are they going to be over here? They're going to be what? What'd you say? Yeah. Note to self, don't ever try that, right? Okay, so what are we going to do here? Sodium what? Sodium nitrate and silver chloride. Does everybody see that? The positive end of one compound has traded places with the positive end of the other compound. Now, will two positives ever come together? No, there ain't no way, right? This sodium and this silver is not going to come together. Electrostatically, they would repel, right? Opposites attract in chemistry. All right. Are we good? Okay, what about this one? And then I'll tell you how do you know if the reaction is going to happen or not, right? Because it's the same situation.